a to the n plus 1, right? That's what you had guessed? Isn't that what you had guessed? And I'm asking you if this answer here is that. So let's plug in 0. Do y'all see what I'm doing? I'm checking to see right now. Does this equal this? Well, let's plug in 0. What do you get when you plug in 0? C sub 0 over 1 times plugging in 0, x minus a. Right? Bear with me. Let's keep going. I know you're already going, we don't have that, but just keep going for a second. What's the next one going to be? C sub 1 over 2 x minus a squared. Do we have that? Yes. Next one, c sub 2 over 3 x minus a cubed plus, that's what we have, right? Yeah. So this appears to work all the way out there, right? It's just this first piece. Distribute c sub 0 through. Right here? Isn't that what you would get? You have it right here. And this right here is a constant. C is a constant, right? C sub 0 is a constant. And A is a constant. So this piece right here that doesn't look like it matches is actually just part of this bigger constant that you put together. So it is okay. So the index does not change. So when you take the derivative and you use the formula, the index goes from 0 to 1. If you integrate, you use the formula, the index does not change. All right? I was just going to make a comment like that. The next example I'm put on the board is kind of where your legs get a little wobbly. Normally, students' legs get a little bit wobbly here. And I couldn't help but think of this video I saw on the internet a couple of years ago. Some guy, I don't know if you've ever seen it, I don't know if it was a fake or not, but it was some guy going into a convenience store to get beer, but he was all like totally intoxicated and like couldn't walk to the cooler and was like opening the door and like falling. Have y'all ever see that? It was like to some music. It was pretty funny. So I don't know. I'm thinking wobbly legs, and that's what came to mind. All right. I want the power series for this. So look, we were doing power series just a second ago, right? And we were doing this. And all of a sudden I said, hey, let's talk about differentiation and integration. And now I'm going to come back to this and say, let's find a power series. And then you're going to go, well, wait a minute. That doesn't look anything like this, right? But why did he talk about differentiation and integration? Right? What is what? What? Differentiate? That? What would happen if I differentiate that? Let me just see. What would the derivative of this be? Let's look at this as being 1 minus x to the negative 2, right? That's what that is? So if you took the derivative of that, what would it be? Negative 2. Differentiate. You said differentiate, right? Negative 2 comes out. 1 minus x to the negative 3. And then derivative of the inside is negative 1. And that's 2 times 1 minus x to the negative 3. Which is 2 over 1 minus x cubed. So it got ugly, right? I mean, it got a little more difficult. Why can't we use this formula on the original problem that's in blue? Because it's squared. So some students will try and get clever and they'll be like, okay, well, I'll square it. 1 minus 2x squared plus x squared. They square the bottom. That still doesn't get you anywhere, because you can't split this up. You have 1 term, 3 terms. You cannot break that up, right? So there's nothing you can do. Now, you said differentiate, and what we got was not any better, or was not this way. So maybe integrate, right? All right, so let's just take a look real quick at what the integral of this is. What is the antiderivative of f of x with respect to x? In other words, what is the antiderivative of 1 over 1 minus x squared dx? Or another way of saying that, what is the antiderivative 1 minus x to the negative 2 dx? What is it? All right, I'm hearing what? I'm hearing this is a candidate? Or no? No? Hold on. Were you saying this? Plus C. Yes, that's the same thing, but is that it? I really do hope that you could integrate this. Basic u sub, right? U to the negative 2, and you could do it. But are we here? Derivative, I'm going to double check it. If I take derivative of this, negative 1 comes out, makes that a positive 1. Power comes down. So I have 1 minus x to the negative 2 times derivative of what's inside, negative 1. Is that?
Yes.
Where's the negative over there? I don't see a negative 1 over there. There's no negative there? So I heard someone say negative 1, so I put it there. Is it that? Take derivative of this. Ah, shit, man. Okay. Let's let u be 1 minus x. This is it, okay? But you got to be able to get to it, right? So u is 1 minus x, right? What's du?
Negative 1 dx.
Negative 1 dx. Okay, I have dx, not negative 1 dx. So I'm going to take negative on both sides. When I rewrite this integral in terms of u, it becomes 1 over u squared. Dx gets replaced with negative du, right? Now, this is negative integral u to the negative 2 du. Power rule on that is negative, okay. Antiderivative of that, you add 1, so u to the, but then you have to do 1 over that. And the negative and negative go away and you get positive. So this is correct. Understand? But this is just 1 over 1 minus x. Ah, I know the power series for that, right? Yep. Yes? So that was just us thinking, all right? I'm just thinking about this, that I know the power series for the antiderivative of that. Think about what I just said. The antiderivative of this, I know the power series of, right? Which means that to get from this power series back to that, I do what?
Derive the series.
I derive the series of this.
That makes sense.
Okay, so it's what a lot of people do is they accidentally integrate the power series for that. That's not what we're doing. So let's try and think about this in this sense. Do you agree with this statement? The derivative with respect to x of 1 over 1 minus x is equal to 1 over 1 minus x squared.
Yeah.
Yes? Because what we said was if we integrate this, right, we get, well, what's the integral of the derivative? They kill each other off. You get this, right? So the integral of this is actually equal to that. So we need to do this. We need to differentiate this power series, and it will give us this power series. Do you all follow that? And, well, it's actually not that bad, because what is the derivative of this power series? Well, what's the power series? Sum n equals 0 to infinity of x to the n, right? That's what it is?
Yep.
Okay, and just use your quick little power rule on that. This is equal to sum n equals 1
Yes.
to infinity n x to the n minus 1. Power rule. Okay? And just for fun, I'd like you to change the index back to 0, just for fun. What would happen if I change this index back to 0? I'm going to replace all my n's with what? M plus 1. Be careful. Because if I put m plus 1 here and subtract 1 on both sides, I get 0. So this is going to become sum n equals 0 to infinity. That n gets replaced with n plus 1. And then x to the what? N plus 1 minus 1, so just n. That's the power series of this. Right there. That's kind of cool, huh? Maybe not. How about this? Find the power series for this function. F of x equals natural log of x plus 5. So yeah, when you look at that, you're like, okay, wait a minute, hold on. I have no idea what the power series is for that, right? Like, that does not look like this at all. But what? Do you know? The derivative of that is something that looks familiar, right? The derivative of this function is 1 over x plus 5, right? Which you could write as 1 over 5 plus x, right? Or you could write that as 1/5, 1 over 1 plus 1/5 x. What the hell just happened there? The wheels are coming off a little bit, no? Just factor the 5 out of the bottom. So I can get it to look like this. Yes?
Why can't you just do the x minus -5?
That's not the formula.
Oh,
It's 1 minus the something with the x in it, right?
sorry, yeah.
So I'm almost there, right? This is 1/5 times 1 over 1 minus negative 1/5 x, right? Now, this was, again, just me thinking, look, I can actually, if I take the derivative of that, I actually know I can turn that into a power series using this formula. So let's kind of back it all up and say that what we know, right, this, what we know, is the derivative of that function, right?
Yes.
This is the derivative of that, which means that we need to do what with this power series to get back to there? Integrate it. If I integrate this, and I'm going to write it this way, so the integral of 1 over x plus 5 dx should be equal to my natural log of x plus 5, right? I think this statement is the one that hopefully makes it make most sense. The antiderivative of this is this. Sure, we know that because the derivative of this is this. This is the thing we know a power series of. So that becomes integral of 1 over 1/5 out here, okay? 1/5, 1 minus negative 1/5 x dx. Pardon? With power series, yes, 0. Well, for this formula, for geometric, it was 0. So now I'm going to do 1/5 times the integral of the power series for this. So this equals 1/5 times the integral sum n equals 0 to infinity of what is the power series for this? Negative 1/5 x to the n, right? Negative 1/5 x to the n. Okay, we've reached a critical point in this problem. A very critical point. In our general formula for a power series, right? The coefficient on x in here is 1, isn't it? This is some constant. We don't really even know what it is, right? But it's a function of n. What I need to do before I can integrate that is I need to write this as 1/5 integral sum n equals 0 to infinity of -1/5 to the n times x to the n. Now the reason I need that is because this piece right here is c sub n, and this piece right here is x minus a to the n. Do you understand? This is like x minus 0 to the n. When we do our formula and we raise, this is going to now be raised to the n plus 1, notice that that is not going to affect this. Do you see that? But if you had not pulled the -1/5 out, it would affect it, and that would mess everything up. Follow me? Okay. If I just say right now, put n plus 1 up here, like when we do the integration, that's going to become an n plus 1. I put a 1 over n plus 1 out here. Then this power affects the -1/5, right? Is now going to be raised to the n plus 1, and this one's going to be raised to the n plus 1. We don't want that to happen because in this general formula, when we integrated it, right, didn't we just add n plus 1 up here and divide through by n plus 1 here? We did not affect that constant. We want the same thing here. This constant we don't want to be affected. So let's just do our integration here. We have 1/5 times sum, n's going to be at what? We're integrating, so keep it at 0. Then what? C sub n. That over n plus 1 x to the n plus 1. I'm going to do, no, guess I could just to kind of make you wonder how this happened. Sum n equals 0 to infinity of -1 to the n times 1/5 x to the n plus 1 over n plus 1. So what did I do? Took a -1 to the n out of this, right? So I rewrote this piece right here as -1 to the n, 1/5 to the n, right? That's what I did there. And then I noticed I had a 1/5 out here, and I brought it back in. And when I put a 1/5 that's on the outside next to this, that's 1/5 to the 1, isn't it?
Yeah.
And now I can put these two together and make it an n plus 1. And if they're both to the n plus 1, if it's 1/5 to the n plus 1 and I had an x to the n plus 1, I can put those together as 1/5 to the n plus 1. There's a lot of little exponent properties happening just from this line to this line. Do you follow them all? I make sure that you can do this, okay? I mean, on your own. A lot of times, like in the back of the book, your answer is going to look like this, and you're like, what the hell, I got this, and it doesn't look exact, you know, but it's the same answer. Now, I just want to try something real quick, all right? I just want to try something. Still saying, this is our answer, okay? I want to see something. Right here, before we integrated, we had 1/5 integral. Let's just write out the first few terms of this right here, just the way it appears. This would be, what, n is 0, we get 1. And then when n is 1, we get minus 1/5 x, right? When n is 2, we get plus 1/25 x squared minus 1 over 125 x cubed, right?
Yeah.
Plus dot, 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 right? That's what we're trying to integrate. Let's go ahead and integrate those. I erased the 1/5. I'm going to stick that one back in here because I want to keep this. This was our answer before I cleaned it up. Integrate these term by term. 1/5 stays out here. This is x minus What does this become?
1/10.
1/10 x squared plus
2.
170, yeah, 1/75 x cubed minus, what is that?
What time is that?
500?
Whatever.
500
Is it? Yeah, it is.
x to the fourth plus dot, 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 right? That's what it is when we integrate it. All right, let's let n be 0 here. What do we get if we get n, if n is 0? 1, right? Negative 1 to the 0 is 1. 1/5.
1/5 x over 1/2.
What is this? If n is 0, we get 1/5 x
Oh, so it's 1 over 1.
over 1. So 1/5 x.
No.
Oh, wait,
n was 0, right? So
No, n is 0. Let me not look at this one, because this one I brought the 1/5 back in. Look at the one right above it, right here. Plug in n is 0 right here. What do you get? 1 over 1 x to the 1, right? So we just get x times a fifth. That's this first one. X, then we have the 1/5 out there. When I let n be 1, what do I get? Negative 1/5 over 2 x to the second, and this is really just negative 1/10 x squared. That's this one. All I'm trying to do is verify that there were two ways I could do this, right? I could just use the formula, but if I use the formula, look, the formula, I have to pull that 1/5 to the n out, negative 1/5 to the n out. If I mess that up, this is dead. If instead I just write out the power series, and then from here, integrate each one, then you get the same answer, don't you? The difference is that this one's not in sigma notation, this one is. Do you think you could put that in sigma notation? Do you think you could? Do you think you could turn that into this? I bet you could. I bet you could. It won't look like that answer I have right there, but let's try it. Can you turn this into sigma notation? Screw all the crap we had over here. Can you turn that into sigma notation? What's happening with the powers on x? They're going up. So let's start at 0 though, okay? So how about n minus 1? That'll start us out, n plus 1, sorry. N plus 1, right? That'll start us out power 1.
Yep.
And then what about all these numbers? Alternating, right? Positive, negative, positive, negative. How are you going to do that? Negative 1 to the n or n plus 1. If we're starting at n is 0, then that'll give us a positive 1 first. So that'll be positive, negative, positive, negative. And what about all these numbers? They're all 1 over what? Those are all multiples of 5, are they? See, this is where you have to recognize what each of these numbers are. This is the hardest part of the whole thing.
5 times 2. No. Yeah, you had this.
That's not so easy. Can you get that? You want to create a sequence of numbers right now, don't you? You want it to be the denominator out here. You want it to be 1, then 10, then 75, then 500. Can you come up with a formula to generate those?
Like 5 to the n.
No.
Okay, maybe we can break down. This is 5 times 2. This next one is what? 5 squared times 3. This next one was 5 cubed times
Yeah.
4, isn't it?
Yeah. So
5 to the n.
5 to the n times n plus 1 will work. All I'm trying to get at here is that there were two paths to the same destination, all right? And you want to be comfortable using each one because sometimes you want to kind of double check. Sometimes they want the power series written out, not in sigma notation. They is however you're, Whoever needs it. I'm going to introduce the next problem. I'm not sure if we're going to be able to get through it all.
I like these.
I have 2 more examples and I have 15 minutes. Okay, let's do this one. I'm going to set up this first one. I think I'm going to let you take this one home to finish. I'm sure that's what you want to do. You got the whole weekend. What else are you going to do? Oh. All right, I'm going to help you get this one going. So there's nothing super obvious about this one. What you have to do first is rewrite this as 1 over x minus 1 minus 1 over 2x plus 1. And how in the hell did I do that? Partial fraction decomposition. So in other words, I took this over here and I realized that this denominator factors to be 2x plus 1 times x minus 1. And then I said, okay, I'm going to try and split this into 2 pieces. So I did partial fraction decomposition to get us to here. We did that when we were integrating, right? Once we're here, I can tweak each of those to look like this, which I invite you to do. Those aren't very difficult problems to work. These are straightforward, aren't they, individually? The heart of this problem is the fact that you have to be like stuck with it for a while and then say, factor partial fraction decomposition.
I like that.
Okay? I won't collect this, but I encourage you to do that one on your own. Okay? Now, the last example I have is much more difficult. But there's a lot of really interesting stuff that happens in this problem. So x squared plus x over 1 minus x cubed. So here's what I'm going to do. First step, I'm going to break this into 2 fractions. That I'm allowed to do because I have 2 terms in the numerator and 2 in the denominator, right?
Yes.
Okay. The next thing I'm going to do is I'm going to pull the x squareds, or the x squared here out in front, kind of like what we were doing before with constants. So far, are we okay? And then we have to realize something. This right here looks like kind of like a problem we just did a second ago, doesn't it? Kind of. I think that that's probably related to this in some way, isn't it? Isn't that related to this in some way? I mean, this is this, right? What's the derivative of this? Yes, go ahead.
Would you have to do multiple intervals
Yes.
and then do the same amount of intervals, or the same amount of derivatives as intervals?
Yeah, let's see. This is this, right? If we differentiate this, right, we should get to something like this. Shouldn't we? Or if we integrate this twice, we should get to something like that, right? So let's try and see if we can make the direct connection on how these 2 things are related. I think what I'll do is is all integrate. Man, we have so many choices here. I'm going to just try and integrate this right here. I'm going to run out of time. You know what? That's perfect. Let's just do that. Look, I want you, forget the rest of this problem. I want you to go home and see if you can find the power series representation of this. Just what's in blue, just this one right here. And my hint to you is that, yeah, it's going to be, this is connected to this right here by two integrations or two differentiations. You have to figure out which one it is. All right? Bonus? You like bonus?
Take that. Yeah.
See, I say homework, do it from, oh man, I'm busy this weekend. Man, I'm working. Bonus, hell yeah, man. I'm all over that. Bonus. I have like a pile of your work that I still have to look at. I keep on adding more shit on top of it.
Yeah, we've been waiting for that too.
I know. Well, you know, it's been a really busy couple of weeks for me. What? Oh. I wish there was an easier way to just do 100, just copy paste all the way.